Okay, so we will continue with the discussions, and I will try now to discuss a couple of input files or a couple of structures, details for the calculations. So just a reminder for a structural data, right? Space group, lattice parameters, and the position of atoms. So if you want to specify the crystal structure of rutile, you would say I have that kind of space group, I have my lattice parameters here in Bohr, I have titanium and 1 oxygen. And of course, 1 titanium and 1 oxygen cannot make TiO2, but if you look now in the international tables of crystallography, you see that the position 0, 0 actually is 2 positions, at 0, 0, 0 and at half, 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 and the position x, x, 0 is actually 4 positions, like this here, it's Markov position 4f, and that makes 2 formula units of TiO2 in this unit cell. A few specific things. In some space groups, there are 2 different settings available. One is with inversion and one is without inversion symmetry. So take, for instance, silicon or diamond. That would be the conventional unit cell of silicon. It's a face-centered unit cell, face-centered cubic cell, where 1 atom is in the origin and another one is at the quarter, quarter, quarter over here. But that would mean in this origin of the unit cell, we don't have inversion symmetry because we have an atom up here, but down there is no atom. As you can see on here on that side, there is no corresponding atom. It's tetrahedral symmetry. However, we can have a different setting where we shift the origin of the unit cell in the middle between 2 atoms, right? As indicated over here. And if I choose this kind of setting, tune your PC, I will not tune it, okay? If you choose this kind of settings, then you have inversion symmetry and calculation runs 4 times faster or something like this, because a multiplication between 2 numbers, if you have real arithmetic, is just 1 cycle, but a multiplication of 2 complex numbers is actually 4 multiplications. Real, real, imaginary, imaginary, and the 2 cross terms. So it takes much longer, and therefore WIEN always will use something like this. Here are a few rules for setting up the sphere sizes. Okay? So they must not overlap, of course, but they should be as large as possible to save time. Typically, we make a radii for S and P elements 10 to 20% smaller than for D or F elements. So that means if I have a compound which has 4 F electrons, 3 D electrons, and S and P electrons, carbon, oxygen, I would make the sphere sizes of the 4F element as big as possible, then the D element a little bit smaller, and the SP element even smaller. It has nothing to do with ionic radii. You would say a titanium 4+ ion is a very small ion, and you would make it a very small sphere. Wrong thinking. Don't think about ionic radii. It's this role because the convergence with the number of plane waves is most difficult with F electrons, then with D, and it's most simple with S and P. Another rule is that the largest sphere should not be much bigger, let's say maximum 50% larger than the smallest sphere. So don't choose spheres of 1.3, 1.2 Bohr and another atom with 2.5 Bohr. That is not suggested because this could lead eventually to linear dependency for this large atom. There is one exception, and this is hydrogen. Hydrogen makes extremely short CH or OH bonds. And therefore, hydrogen you would use a sphere size of only around 0.6, and the carbon or oxygen would be twice as large as the sphere of hydrogen, roughly speaking, okay? And this is also important, hydrogen converges very, very quickly in terms of plane waves. So an RKMX of 3 is usually by far sufficient to converge the hydrogen wave functions. Also, they have these small spheres. Another important thing is you should not change the sphere sizes in a series of calculations, because this might lead to small numerical differences, and total energies will be not directly comparable if you use different spheres. Okay. About the program structure of WIEN2k, we already discussed that. Remember the day file or the standard out, where you saw all those programs for the initialization. Just remember these first three programs do, so to say, the symmetry, the geometry detection of this. This is the atomic program doing 3 atoms, K-mesh, and then the superposition of the atomic densities to get the crystalline density. And then you have this series for the SCF cycle, and we discussed already what these programs do, I think, in the first lecture, so I can be fast here. I told you about this most important RKmax parameter here. That is the convergence criterion, and Kmax is, as I said, the maximum K value in a plane wave expansion of the wave function. So this Kn runs until Kmax is met, but the convergence is not Kmax, but it's the product of the smallest sphere size times Kmax, because it scales with this product, basically. Here you have a table that is also on the website. What is a required RKmax if your smallest element is whatever it is here? So for hydrogen, you need only RKmax 3. For carbon, 5.5 should be okay. But if you are using osmium or whatever, lutetium or the 5Ds or 4F or 5F electrons, then better go up in RKmax. Okay? Be careful with these numbers. Increasing RKmax by 10% doubles the CPU time. That doesn't really matter for titanium carbide, whether it runs 3 seconds or 6 seconds, who cares? But if a calculation takes 1 month or 2 months, you better choose these values very carefully. Okay? In general, strategy is always start with small RKmax, do all the structural relaxations and all the main calculations first with these small values, and only at the very end increase them and test them if this was sufficient or if anything else has changed. That's the basic strategy. Okay? If you do a structure optimization and the atom has to move for 1 angstrom around, this will take many, many SCF cycles, hundreds of SCF cycles. If you do this with small RKmax, you are extremely fast doing it like this. Also, it might be inaccurate, but then you do it first, the movement of 1 angstrom with this small RKmax. When you are done, you increase RKmax and move then hundreds of an angstrom maybe to the final result. That's the strategy to be efficient. Brillouin integration Fermi method. So in order to calculate the charge density, we have to take this summation over all occupied bands and integrate over the Brillouin zone, and we replace this integral by a sum with some weights of the square of the wave function. These weights depends on K and on the band index. So first of all, for full bands, the weight is given simply by the symmetry. So just look here on a 2-dimensional Brillouin zone, then it's clear the gamma point in the center of the unit cell appears only once and has therefore the weight 1. An X point appears 4 times, but since it's on a surface, this is only half, so it has a weight of 2. A delta point here would have a weight of 4, because it really appears 4 times if this is a square. And a general K point somewhere in the middle would have a weight 8, because it appears 8 times in this in this squared 2-dimensional Brillouin zone. If I use a certain density, so here for instance a 5 by 5 mesh, that would give me without symmetry 25 k points, right? And the distance here determines the quality of this calculation. And therefore one can do a trick and use a shifted Monkhorst pack mesh. Instead of using those points, you would use the black points. And then you see I have only a 4x4 mesh, so only 16 k points, and have the same density of k points then with my 25x25 mesh. What I avoid is to calculate low weight points like the gamma point or like the surface points, which have anyway in an integral only a very low weight, but I'm trying to use higher weights k points, and therefore I'm more efficient having the same accuracy. This is fairly simple for an insulator because a band is either full or completely empty, no problem. For a metal, we have partially filled bands. We must find the Fermi energy. That means we have to integrate all our states up to the number of Na, the number of electrons, and then determine the weights of each state E, K, and N. That means now on a gamma point, not all occupied states might have the same weight on a certain point, but near the Fermi energy they could have a lower weight if they are only partially occupied, so to say, in a metal. To determine this, we can use the tetrahedron method. That is our default. Actually, the tetrahedron method with the Blöchel correction is our default. And that is, so to say, I would call the best scheme, integration scheme, at least for t equals 0, which you can do for a three-dimensional integration. However, sometimes people want to accelerate integrations with metals, and then they use some broadening methods, either Gaussian broadening or more physically, if you want, a temperature broadening with a certain broadening or temperature factor. So just remember 2 millirydberg, so 2 here, would correspond to room temperature. So there is not much space for broadening, because otherwise you are doing calculations at very high electronic temperatures, basically. But still, these broadening methods are good for 2 reasons in particular. So first of all, for difficult to converge cases with F electrons, metals with F states, flat bands, broadening helps a lot to damp these SCF oscillations. And secondly, if I have not a 3-dimensional integral, but only a 2-dimensional integral. When could I have a 2-dimensional integral only? In which kind of problem? If I want to simulate a surface or a graphene sheet, a single sheet, right? So if I want to simulate a 2-dimensional material, then my Brillouin integration is effectively only a 2-dimensional integration, not a 3-dimensional one. And if you form tetrahedra on a 2-dimensional system, that are all triangles, they are all degenerate, and that can lead to problems with the tetrahedron method. So then you use temperature broadening, but be careful. The bigger you make this number, the faster the calculation will converge, for sure. But if you make this too big and you have a magnetic compound, you may even lose or at least reduce drastically the magnetic moment. Okay? So if you use and do a calculation for nickel, FCC nickel, with a large temperature broadening, often in literature it's said we use a broadening of 1 eV or so, sometimes in papers. If you would do nickel with 1 eV broadening, you would have half the magnetic moment of its actual moment only. Yeah? So this is a potential dangerous thing. It converges very fast, but you occupy unphysically unoccupied states, basically, and that is not what you should do. This K-mesh is generated with this program KGen. We use symmetry, and we automatically always add inversion because we have time inversion symmetry, except in magnetic spin orbit calculations. We'll hear a little bit more, I think, on that point anyway by Javier. Usually you should use this shifted K-mesh, this Monquard-Bach mesh, but if you are interested in gaps, these gaps are often at gamma. So what you read from the SCF cycle for the value of gap might be too large than what you really have if the gap is at gamma and gamma is not in your mesh. Then you should use the gap value of the SCF file only as a first hint and really plot the band structure and look what is the gap at gamma and read it up from the band structure. How many K-points should I use? As I said, it is not so easy to answer. General rules: small unit cell, metals, large K-meshes. Let's say 1,000 to 100,000 K-points. Large unit cell and insulators, 1 to 10 K-points, typically. Again, the recommendation: use first a fairly coarse mesh for SCF and for structural relaxations, and continue later with a finer mesh. If you have enough cores, you do K-parallel calculations anyway, so always use then a couple of K-points, except you have really large unit cells. And it's of course very often done that you do an SCF cycle with a coarse mesh, but for spectrum or density of states or so, use a very fine mesh. In one of the exercises in the optics of aluminum, you should do this. For instance, you do a normal SCF calculation, but the optics of aluminum converges only with very, very large K-meshes, and we do this then specific for the optics calculation, a finer K-mesh. No need to repeat this SCF cycle for that. Yeah?
And how much is a small unit cell? I mean, for example, can you give me an example?
So titanium carbide had 2 atoms per unit cell, and I was using 1,000 K-points. I would say this is the minimum what you should use. A better calculation should have 10,000 K-points for this. Okay? And the K-mesh basically scales with the number of atoms. So if I say 1,000 for 2 atoms, and I have now 20 atoms, then use 100 K-points as input. Okay? That's rough estimate. It depends a lot on the specific property. I mean, this optics example for aluminum will be something where you really need a huge K-mesh to do this. Or if you do NMR for metals, you need, as I said, millions of K-points eventually. For some other properties, it's no problem at all. You can do silicon, which also have only 2 atoms, structure optimizations with 1 K-point almost. Doesn't matter. Yeah? Of course, your density of states with 1 K-point will not look nicely, right? That's also clear.
The number of K-points, yeah? the direct unit cell gets bigger, the reciprocal gets smaller. And what you need is a constant mesh in the reciprocal space. So if the unit cell in the reciprocal space is small, you need few K-points. And for the large unit cell, if you have a large unit cell, a small unit cell in direct space, you have a large unit cell in the reciprocal space.
So typically, if I have a unit cell, let's say with 100 atoms, I use only so few K-points as I have cores anyway. So if I have a PC, for instance, let's say with 4 cores, I would use a K-point mesh that it does not produce more than 4 K-points. That is by far enough. But it's no use to have only 1 if I have a computer anyway, which can do 4 calculations in parallel without extra costs. Then I am always using these 4, for instance.
And for the large unit cell, is there any, for example, influence of on K-point if you use an even K-point or odd K-point?
This could be an influence, of course. Yeah.
So which one, for example?
But that depends on your Brillouin zone, or for metal, what is occupied or not. You cannot say which one is good. No, there is this. For metal, it really depends on the details of the band structure, right? Where is it metallic? Is it just metallic around gamma, or is it everywhere? Are there many bands crossing, or only at gamma, or only at the Brillouin zone edge or so? Every band structure is different.
So if we use a k-point tree and 4 is the big gap and discrepancy between the results? Or
test it. You have to test that. There is no rule. You cannot say 3 is better than 4 or 4 is better than 3. No way. You increase your K-mesh until your result which you want to publish does not change. Okay? That's the only rule which appears. Okay? And with time you will get experience so that you start with some reasonable thing and don't do unreasonable things. I mean, starting titanium carbide with 10 K-points is a stupid thing. Okay? But starting titanium carbide with 1,000,000 K-points is also an unnecessary thing, so to say. Yeah? So these are guidelines for starting, so to say. But that does not tell you anything, in particular then for certain properties. It can well be that the structural relaxation is fully converged, but an electric field gradient is not. You need more K-points, or some other quantity is not. So it, yeah. Huh? Good. The programs are all executed in Wien with a master shell script. It's called X LAPW, but we always do a shortage of only using it X, calling the program number and name and then some switches eventually, so this would mean spin up and with an orbital potential, and this X script generates a definition file called LAPW2.def, and in this def file there is a relation between a unit number, because Fortran reads from numbers, from unit numbers, and the actual file name. It also says whether this file must exist, this input file must be there, otherwise the program will stop, or whether this file can exist or does not exist, it doesn't matter, or something like this. And after it creates this definition file, which you can always look up later on, it executes the program and this definition file and executes this way. So this is the way WIEN2k basically works. All the WIEN2k shells have a long and a short name. So all scripts have a name underscore LAPW, but always also a short name like X or run SB or run FSM instead of run FSM underscore LAPW. And all scripts have a help switch, -H, which gives you the meaning of those switches here. Okay, just can simply execute it like this. When you do an SCF cycle, the command would be the run LAPW. A few options we already have discussed, for instance, these convergence options over here, right? You can do parallel calculations. You will do this in some of the later exercises. You can use iterative diagonalization for large cases. And large means more than 50 atoms. So nothing here at this exercises. We don't have such a big example here for time reasons. But this iterative diagonalization will give you a large speed up. And large means up to a factor of 10. So when you really do a calculation with 100 or 200 atoms per unit cell, use this iterative diagonalization. It will take 2 weeks instead of 20 weeks. Okay? So don't forget this switch. Forget it for titanium carbide, of course. No use. You can add spin orbit. We will hear more of this. The programs automatically detect whether we have inversion symmetry and call then either a program LAPW1 or a program LAPW1C, depending on whether we have inversion or not. This is the real or the complex version of the code. And all the master output of the SCF cycle is called case.scf and contains the history of all the cycles, and the information, the important information, is always stored with some labels. And you can always grab after label with a colon at the beginning and then the SCF file name. So you can grab for energy, for charge distance, for the Fermi energy, the gap, the charge inside the sphere, number 1, and so on. You can grab for forces, There are two differences. It's in Cartesian coordinates here, 4, or in global coordinates in FGL. And there are a couple of other labels which I'm not mentioning, but they should be self-explaining basically what they mean. How do I get help? We have this -H switch for scripts. There is a command help LEPW, which simply opens the user's guide in the PDF reader, and then it's suggested that you use search command, Control F for instance in Acrobat, and a keyword which you should think of yourself to find the specific item in this user's guide. So if you want to know how is the input for LEPW5, you should remember the input file for LEPW5 will be called IN5. So search a couple of times for IN5 until you find the section. After 3 or 4 searches, you will find the section where IN5 is described in detail, and you read through this section to find the required details. There is on our website, under registered users, there is a frequently asked question page with answers to some common questions. There is update information about the newest version. Usually we release once a year a new version with bug fixes and new features. So one should from time to time upgrade WIEN. There is a textbook section, Hans mentioned that. There is for beginners this nice book from Stefan, and one should probably print that out, take it at home and read it every night before you fall asleep. You will then fall asleep quicker, so it's okay. It's the same with the user's guide. You should also read the user's guide. You will fall much faster into sleeping. Okay, and there is a mailing list. You have to subscribe to this list. So without subscription, you are not allowed to post questions, but you should first search the mailing list. Maybe your question was already answered. So if there was a question like, can you explain me what means ABC in this input file, and there was an answer, and 2 weeks later you come again and ask the same question, you most likely get, if you are lucky, no answer, and if you are unlucky, you get a very unkind, unfriendly answer, right? So search first. There is a very efficient Google-based search algorithm there. Search for your keywords. Maybe you got already this answer in the digest. And if you post questions, you have to provide sufficient information. A question like, my calculation crashed, can you please help me, will basically end up in the waste bucket of every email, incoming email, because what should we do with this question, right? I cannot help you if your calculation crashed if you don't provide me with details. A lot of details, and it's your responsibility at least to find out what are the details. I mean, where did it crash? What was a possible error message, and all these kind of things. So check these files, all those files, to locate your problems, and at the bottom of those files usually there is some information given. And if you cannot interpret this information, then ask. That's fine. But without this information, nobody can help you. The most common problems, I would say, is a message like QTLB value too large, stop. So your SCF cycle stopped during this. Again, first of all, you have to identify in these output files for which eigenvalue, which atom, and which angular momentum, which L, it happens. This is an information we need to know, otherwise nobody can help you again. Then you have to identify the corresponding linearization energy in the SCF file and eventually change the linearization energy in this. But I should say 80% of these errors are because your structure is wrong. Meaning you have input instead of angstrom Bohr or mixed Bohr and angstrom, you have not TiO2, but only you have TiO7 or whatever in your structure, whatever, some stupid mistake made, then typically this also appears. Okay? But there are a few cases where these errors can happen, and we know how to fix this easily, but we need this information, and then we can tell you what you should do, basically, on the mailing list. Okay? SCF cycle may not converge, eventually diverge. I would say with modern mixers, it does not happen very often anymore. If it really happens again, in 90% it's because you have a wrong structure. There are still cases with many F electrons or so which could be difficult to converge this, and then you may get help eventually or some tips. It can sometimes be a little bit tricky, but only in difficult cases, and difficult means metallic cases with many degenerate atoms with D or F electrons at the Fermi level. So if you do a surface with 44 F electron systems with partially filled 4 F electrons, metallic, this will be difficult. And then you may encounter this. Otherwise, if the SCF cycle was not converging in 40 cycles, you simply would continue. Submit another 40 cycles. By default, we run only 40 cycles and stop there. Then, whether it's converged or not, it will stop. And then it tells you SCF not converged. That doesn't matter, just check whether the convergence was okay, distance was going down, it hasn't reached what you wanted, then you submit another job and run 40 more cycles, basically. Good. About the input files, case IN1, the input for LEPW1, the most important parameter is this RKmax. In the second line, this number 7 here, and you could put here a smaller or a larger number eventually. That's key if you want to check convergence. Another thing is this Lmax, which you never change. This is this Lmax in the expansion of the spherical harmonics expansion inside the sphere. Don't put this smaller than 8. Then your calculation is definitely wrong. 8 eventually would be possible, but you saved a small fraction of time only. And this 4 means the maximum L in the non-spherical matrix elements. I don't want to discuss this more. More important are these energy parameters. So remember what Heinz told you in the morning. We are using a radial wave function which depends on energy, dependent on L and the corresponding energy. And in the input, this input file, you are saying where the energies are set. In this input file, you find the Fermi energy, which is updated automatically always. And whenever you see a number 0.3, that means that this 0.3, the program will change to the Fermi energy minus 0.2 Rydberg. That means we have the highest occupied orbital, and we put this linearization energy then 0.2 Rydberg below the Fermi energy. That means in the middle of the bands. That should be a good approximation or a good setting, and this means this 0.3. There are some other things, like here you see 2 zeros here. That means for L equals 0, we will add a local orbital at a much lower energy, minus 3.7 Rydberg, but with some search, I come to this. But if you see 2 lines, it means we have a local orbital. That means we have these semi-core states, like in titanium, the 3s, and for the p, the 3p. Okay? So for D, we have only 1 line, but for S and P, we would have 2 lines if we have these semi-core orbitals, like in titanium 3s and 3p. If we have this, we usually don't take this value. This is just a starting value, but we are searching with this number for what we call an A top and a bottom. What does that mean? Now suppose this is a density of states, then you have somewhere a beginning of the band and the top of the band, and a good energy would be to put the energy parameter in the middle of the band. So how do I find this a top and the bottom without doing the density of states calculation? Then I would know where it is. You remember these band ranges we discussed? Then I would know where I should put that. But before I do the calculation, I don't know that, and I have to put that in the input. So what we are saying is this A bottom corresponds to a bonding state. And the bonding state between two atoms would have slope 0 here at the sphere size. So suppose you would have two atoms, one atom here and another atom on that side. A bonding wave function could look like this, right, schematically. Slope 0. The top of a band corresponds to an anti-bonding wave function. How does an anti-bonding wave function look like? It looks like this. Has a node here and would go here like this with a minus sign to the next atom. So this would be an anti-bonding situation, and this would be the bonding situation. And obviously, the radial wave function changes with energy in such a way, going from here all the way down up to here, schematically, right? I mean, this is only true for the hydrogen H2 dimer, the way I plotted here, but schematically it looks exactly like this. That means we are searching very quickly for energies where the radial wave function has either slope 0 or value 0, and that gives me the values of a bottom and a top, and with the arithmetic mean of these two values I get my mean energy, band energy. This works surprisingly well and gives a very, very good and stable estimate of these semi-core energies and solves this problem. Okay? This 1 here or this 0 means whether we are using LAPW or this APW plus small LO basis set, which Heinz mentioned also at some point. And in the last line, we already changed this. You have here an energy range. You can change this A max here if you want higher bands for unoccupied states. Okay. In the K-list, I think we already discussed that. WIEN2 file. Here you have the number of electrons. So for some spectroscopy with core holes or so, you may need to change this number eventually. This is one thing. And you have here the LM values in an angular momentum representation, symmetry adapted. I'm not discussing this. This is the Gmax of the charge density Fourier series expansion. And this I'm not discussing, but what I wanted to discuss is this tetra and this value. So you would change eventually this tetra to temp. You see the suggestions here, and change this 0 to a small temperature like 4 millirad/Birth or something like this, typically. Okay? That was this temperature smearing instead of the tetrahedron method, in particular for surface calculations. Good. So, bands, density of states, we discussed, I think. Here is the explanation of these partial charges, QTLs. So we decompose a charge of one atom, which is by definition 1, if I integrate it, into a charge outside the spheres, and the sum over all atoms times the atomic and L-like partial charges. And in the density of states, you weight now each eigenvalue with the corresponding weight of atom T and angular momentum L. And of course, even if you plot the total, you are usually not adding this contribution. Therefore, the sum of the atoms does not give you the total loss. Right? Good. WIEN has something special also, which I should mention, that is called the local rotation matrix. That means we have a crystal like rutile TiO2, which is tetragonal. Then you would usually say, this is my x-axis, this is y, and this is the z-axis, the tetrahedral axis. But if you look carefully, you see that there is a coordination of this atom in one direction, but not in the other direction. So these two oxygen, they sit on this diagonal here, but in this diagonal there are no atoms. That means if I rotate my coordinate systems by 45 degrees with such a rotation matrix and define this as x and y, then x and y is really physically different. A py orbital points from titanium into the oxygen, and the px orbital is normal to that direction. If I would keep my original unit cell coordinates and say this is px and this is py, a bond of a py orbital would always be a mixture with this oxygen. Sure, you cannot decompose and you cannot analyze your symmetry in a way I have done over here. And for this local rotation matrix is important, because only then you can make this chemical interpretation of bonding states, anti-bonding states, and so on. Instead of using LAPW2 minus QTL, you can also use an extra program QTL called XQTL, which can make splitting also for F orbitals, can make splittings for arbitrary coordinate systems. So you can rotate your coordinate system arbitrarily as you want, for instance, in an approximate symmetry, in a distorted crystal, to get, for instance, also in TiO2, an approximate octahedral coordinate system, if you use this like that. Also, since it's tetrahedral, that is not an exact octahedron. But as an approximation for interpretation, this might be useful. And you can also use this QTL for splitting of P1/2 and P3/2 relativistic bands. Good. When did you want me to stop? Now? Okay, yeah? Okay, let's do the atoms and molecules, and then we do the structural part tomorrow. I think this is good. So there is one theory which originates here in McMaster's University by Richard Bader, and he tried to define an atom. What is an atom in a compound? So the electron density of C2H4 looks either in a contour plot like this or in a 3D plot like this. So if I want to know the charge of hydrogen or carbon, what is a hydrogen? Now, obviously, this charge is probably hydrogen, but what is this charge? Is it carbon? Is it hydrogen? Who knows what this kind of charge is? Okay, so he found a way to at least define it in a unique way. First statement. Second statement, he also tried to analyze the electron density between two atoms, mainly at the minimum here, and find out from the properties of this electron density whether it is an ionic or a more covalent bond. And this is characterized by what is called the bond critical points, where the gradient of the density is 0. So this would be such a bond critical point. And the value of the Laplacian second derivative at this quantity gives me information about an ionic or a more covalent bond. This is only a rough estimate. It's not absolute values, but it might be useful for interpretation sometimes. And the other thing he did is he defines an atom as a region with zero flux surface. Grad rho times n should be 0. Sorry, this is not coming out properly here. That means here we have again our electron density of this C2H4, and the zero flux line are now these lines here, showing like this, and this middle line over here. That means an atom, this is my hydrogen atom, this stupid object here is my carbon atom, and the other thing is clear. You can see that atoms are very, very different. Take the electron density of CH4, that is basically almost spherical in total. A hydrogen atom would be this, cutting out this small fraction here, that would be the hydrogen atom, and this object is then the carbon atom. On the other hand, in lithium hydrogen, also a sphere, the total density, the lithium would be this small stuff, and the hydrogen would be this one. So you see, what is an atom? Hydrogen can look like this or can look like this. It's not so unique, not so easy to define with spheres or with any other concept. This at least is one absolutely clearly defined concept. Whether it makes sense or not is a different story. It definitely gives you better charges. So here would be the estimate for titanium carbide. It would have a charge transfer of 1.7 electrons, for instance. Okay? But it's not always working. So if you do the same thing for potassium chloride, you get only a charge of 0.6, and that means it's basically less ionic than titanium carbide, which I don't believe at all, let's say. Yeah? So it is a better number instead of charges. So if you take only these integrals over spheres, you get charges of 0.1 or even less if you're unlucky. This gives you some reasonable looking values, but use them carefully. So, good. How to calculate this is described here, and with this I will stop after the Fermi surface. That can be done with X-crystalline, and you have an example of Fermi surfaces with this. Good, and I'll stop at that position. Questions? Quick questions to that?